So hello everyone,
I really
my
could
name is
have
Stincy.
and today I'm gonna
much sooner
give you the solution to exercise 17 to 20 of our second homework day of data representation. We're gonna go through every exercise, and before solving it I will give you the theory behind each exercise. What do we need to know in order to get the result of each exercise? So for our first exercise, exercise 17, convert the ASCII string 9.75 to its hexadecimal representation. Only represent the character between the quotation marks and assume it's a null terminated string. So this exercise basically tells us to convert 9.75 from ASCII to hexadecimal and assume it's a null terminated string. Now, how do you actually convert ASCII to hexadecimal? Well, you use something like this. You're right, that's a converting table. Now, we don't really have a way to calculate from ASCII to hexadecimal, hence why we use a table. It's the simplest way. So let's start by noting down some important information first. So we got the string 9.75 and we have to convert it from ASCII to hex. In addition, that it's a null terminated string. So by using the table, we know that 9 in ASCII is 39 in hexadecimal representation. I'm just gonna write here, this is ASCII, this is hex, and for the dot, it is 2e. For 7, it's 37. For 5, it's 35, and for the null, it is basically just 0, 0. And so we can write the hexadecimal conversion down, and that will be the answer of our exercise. So we got 39, 2e, 37, 35, and 0, 0. And that is our answer for the first exercise by converting ASCII to hexadecimal of the string 9.75. Moving on to exercise 18. Convert the following binary code into an ASCII string. And it's a very long string that I'm not gonna read. Now for this exercise, we have to know some important information. Now bits or bit is just for every single number that you see here, for every 0 or 1 that exists here, it's called a bit. And an ASCII string is represented by an 8-bit string. So in order to translate or to convert this binary code to ASCII string, we have to basically cut this very long string into many 8-bit string. So let's do that. Like before, we note down some important information. I've already noted down here. And we have to cut it into many 8-bit string. And so, yeah, I've already done that. Now, you can just use another conversion table to, well, translate this from binary straight to ASCII. But to me, I feel like using a binary to ASCII table is very time consuming and it hurts my eye. You have to very carefully compare each bit to, well, get the desired answer. And I don't really want to do that. And so for this exercise, I will translate from binary to decimal and from decimal to ASCII. Now it might be longer, but in the long run I guess it's better. So let's do that. So from binary to decimal, let's write it down here. Decimal. Now we can see that there is 1 at the 4th, 5th, and 6th location, and so we can basically write 2 to the power 4 plus 2 to the power 5 plus 2 to the power 6. Now if you're curious about what's the math behind this, I would suggest you go search up how to convert binary into decimal. And so from this equation we can calculate that 2 to the power 6, its decimal representation is 112. And we do the same for every single other 8-bit binary string. And for this we got 49, and this we got 51, for this we got 115, and for this we got about 0. And from decimal we can use the conversion table that we used before. And so 112 in decimal is P, small p, in ASCII. Let's write down here, ASCII. 49 is 1, 51 is 3, 115 is S, and 0 is basically a null termination. And so for the answer to this exercise is, well, we just rewrite the ASCII that we translated, which is P13S. And that is our answer for exercise number 18. Continue with exercise 19. Assume a color display using 8 bits for each of the primary colors, red, green, blue, per pixel, and a frame size of 1280 to 1024. A. What is the maximum size in bytes of the frame buffer to store a frame? And B. How long would it take at a minimum for the frame to be sent over a 100 megabits per second network? And well, there is a lot to unpack here, so let's do that. First of all, the frame size of 1280 to 1024, we can calculate the total pixel of the screen by just multiplying these two numbers together. And the first question asks us to calculate in bytes. Now 8 bits equals 1 byte. So, well, keep that in mind. And let's move to the demonstration, the solution. And well, from the exercise, exercise, it gives us the resolution of the screen is 1280 to 1024, and what we know that 8 bits equals 1 byte. That's just a conversion that we need to know. So for our first question, A, it asks us to calculate the total bytes for the frame buffer. And so now to calculate the total bytes, we need to know the total pixel of the screen and how many bits are there for each pixels on the screen. So let's do that. Now the total pixels is equals to the width of the screen multiplied with the height of the screen. Now the width and the height we already know from the resolution. The height is 1280 and the width is 1024. And let's substitute that in. We get 1024 times, what is it again? 1280. 1280. And we got 1,310,720 pixels. Now that's the first part. Moving on, we have to calculate how many bits are there per pixels. And now we know that for each pixels there are 8 bits for every color, which is RGB, red, green, blue. And so we can calculate the bits per pixel by multiplying the number of bits to the number of color that it has to display, which is basically now bits per pixel is equals to 8 multiplied by 3, which will get 24 bits for every pixels. And so from these two information, we can calculate the total. We can calculate the total bits for the screen buffer, for frame buffer actually. Now the total bits is equals to the total number of pixel times how many bits are there per pixel. And so we already know that there are 1,310,720 times 24 bits per pixels, and it will give us the answer, not the answer, well, it is the answer of 31,457,280 bits. Now this would be the answer for the question A if it asks us to calculate in bits. Now it actually tells us to calculate in bytes, not bits. And we know that 8 bits equals 1 byte. And so, well, we can calculate the total bytes is equals to the total bits, divided by 8, which is, well, the 31,457,280 bits divided by 8, which we got 3,932,160 bytes. Now this is the answer for question A. Moving on to question B. I'm just going to put right here. I think that's good. Now for question B, it tells us to calculate the time to send the frame over a 100 megabits per second network speed. And well, we already know the total bits from before is, well, 31,457,280 bits. And we know the network speed is 100 megabits. 100 megabits is basically 100 million bits per second. So 100 million bits per second. Now, to calculate the time to transfer the data, it basically equals to how many bits you have over what is your speed. It's like the equation to calculate the velocity, which is the distance over time. And so for time to transfer, it's equals to the total number of bits over the network speed. Which is equals to, I'm not gonna rewrite the number again, I'm way too lazy for that, but our answer is approximately 0.314 seconds, and that is our answer for question B. And moving on to our final exercise, exercise 20. Given the two 16-bit numbers expressed in hexadecimal representation, x ABCD and x FEED, evaluate the following expression and give your answer in hexadecimal: x ABCD and not x FEED. Now, I believe that this exercise is very hard to convey its theory by words, and so let's move on to our demonstration screen for an easier time. So for this exercise, it is given that we need to solve the equation x ABCD and not x FEED. So first we could try to convert the two hexadecimal numbers given into binary. And so using our binary conversion table, we know that A is equals to 1010, B is equals to 1011, C is equals to 1100, and D is equal to 1101. And for FFED, we know that F is equals to 1111, E is equal to 1110, D is equals to 1101. Now you may ask, why don't I, what is the meaning of X here? Why don't I convert it from hexadecimal to binary? Well, you can understand the X here is basically a notation. And basically anything that goes after this X is a hexadecimal representation. Now we could really just write ABCD, but it could maybe mean hexadecimal. Maybe it could mean ASCII. We don't know that. The computer doesn't know that. That's why we have to got the notation or something to represent that this string of ABCD is hexadecimal. Hence the X at the leftmost position. It could also be write as OX, though in this exercise it's just X. So continue with our exercise. Now that you know why I don't convert the X into binary, we could rewrite these two numbers in binary form. So X A B C D is written in binary as 1010, 1011, 1100, and 1101. And for XFED, it is 1111, 1110, 1110, and 1101. Now that we got the hexadecimal representation, and no, the binary representation. Now we could start with the operation. Let's start with the NOT operation, since it's in a quotation bracket, right? Bracket. It's in a bracket, so NOT FED. And so right, one NOT operation. So what does the NOT operation do? Well, it basically just inverts all bits. What does that mean? That means that every 0 is turning to 1, and every 1 is turning to 0. And so we already got XFFED. Oh, hang on. Let's copy this and paste it below. Now we can basically rewrite XFED in the FED in the NOT operation. So NOT XFED is, well, you turn every 1 into 0 and every 0 into 1, so it's 0 0 0 0 0 0 0 1 0 0 0 1 and 0 0 1 0. That is the answer to the NOT operation. Now let's move on to the AND operation. AND operation. So AND operation. You know, in programming language, or well, in the programming field, we have the while loop and the for loop, where you use AND when you want when there are 2 or more conditions that you want to met, and if those conditions are met, then something happens, something in your code happens. And I think it's kind of similar here. The AND operation is basically this table: 1 and 1 equals 1, 1 and 0 equals 0, 1 and it should be 0 and 1. 0 and 1 is equal to 0, and 0 and 0 is equals to 0. Now I kind of just understand this as simply they are the same number, so they equals to that number, like 1 and 1, they're the same number, so they equals to 1. 1 and 0, they're not the same, so they don't result in anything, which is 0. 0 and 0, they're the same numbers, so they equal 0. Now, let's do a small example before we come back to the main equation. Let's say we have 0, 1, 0, 1, and 1, 1, 0, 1. So how would you do this kind of calculation operation? We basically just match the pair in the same location, and using the condition that we already got in this little table. And so it is 0 and 1, which is equals to 0. 1 and 1, which is equals to 1. 0 and 0, which is equals to 0. 1 and 1, which is equals to 1. So let's apply these into our exercise. Let me just do this. No, not you. Alright, copy, paste it down here, and then we take the not xfeed, copy, paste it down here. Let's delete some stuff, and yeah, we good. And now the exercise basically tell us to do the operation xabcd and not xfed. So let's align this first. Now we got 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 and 0 0 0 0 0 0 0 1 0 0 0 1 and 0 0 1 0. Now let's calculate this. 1 and 0, which is equal to 0. 0 and 0 is equal to 0. 1 and 0 is 0. 0 and 0, which is 0. 1 and 0 is 0. 0 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. And 1 and 0, 0. And 0, 0, 0, 0, 0, 0, 0. And that is our AND operation. Now, from this, we can solve the equation by converting this this binary string into hexadecimal again. So that's the third part, I guess. Decimal. I know, it's not decimal, sorry, it's binary. It's binary back to hex. And I guess we're going to jump over here. Now we got from the AND operation, we got our new binary string, which is 0 0 0 0 0 0 0 1 0 0 0 0 and 0 0 0 0. Now 0 0 0 0 in binary is 0 in hexadecimal, and 0001 in binary is 1 in hexadecimal. So this is binary, this is hexadecimal, and so we can rewrite our answer to the equation in hexadecimal representation as 0, 1, 0, 0. We could write it as x 0, 1, 0, 0, and that would be our answer to our exercise. And that is the end of, well, my solutions to the 4 given exercise in data representation. Thank you so much for watching. Oh boy, this video actually took me maybe 1 hour and a half to make. God damn. Like, I gotta tell you, this video is literally so scuffed. Like, only when I am halfway recording the long ass video do I realize that there is much more to improve. But then again, it's on me for putting myself in this time crunch. Our deadline's in 2 days, and well, we also have exam in this weekend. So yeah, I don't have much time to lose on these simple exercise anymore. Yeah. So anyway, once again, thank you so much for watching.